Our fix for add last, it works, but I don't think it's as pure or as beautiful or as simple as the somewhat strange idea I'm about to explain. So we're going to introduce something known as a Sentinel node in a moment, but I want to give a little bit of motivation. Code that has special cases is hard to reason about. Human beings only have so much working memory, so whenever you have code that requires you to be thinking about exceptions to the rules and so forth, it's just harder than something where everything behaves in one consistent way. So this is all going to seem a little slippery until you get a little practice, but I hope this example I'm about to show you gives you some flavor for why these kinds of ideas actually make code simpler, even though at first they may seem crazy. So what am I talking about? Well, the fundamental problem here is that when we write the add last method, the empty list has a null first. So there are some lists where the value of first can be null. And that runs us into trouble at this line of code. If the list is empty, then p gets set equal to null, and then we say null.next, and that's real bad. We get a null pointer exception. So our fix to this problem that we have so far is ugly. It has a special case, and this is a list. It's super simple. But if you start moving on to data structures like trees or something with multiple links, you're going to run into huge headaches as you have potentially an exponential number of special cases you have to deal with. We want one consistent story, not a bunch of separate little rules. So what we're going to do to make one consistent story is we're going to make it so that all S lists, even if they're empty, should somehow be the same. They should have the same structure, the same something. And finding that something is sometimes tricky, as we'll see now. So my solution to bring everything together, to bring us into harmony, is going to change the whole rules of the game. I'm going to say, hey, you know what? An empty list is not going to have a null pointer. Instead, it's going to point at a node that I'm going to call a sentinel node. A node that's always there, something that's going to stand there and be the front of the classroom, the first person in line. We know they're there, they're dependable, and we don't have to worry that maybe they don't exist at all. They're always going to be there. The empty list, therefore, is just the sentinel node. It's our faithful companion waiting for other data to get in line behind it if anything ever shows up. By contrast, the three-item list has the same faithful companion, and now the usual recursive naked data structure, 5, 10, 15. So what we're going to do now is try to implement this using the sentinel node idea, and I hope you'll be able to appreciate just how cool this is. So instead of first, I'm going to call this thing Sentinel. Okay, I think it's just a better name. I'll make a little note here, mostly for us. This would be a strange comment to put in code. The first item, if it exists, is at sentinel.next. Okay. So we can see that if we look back at our picture from the previous slide, sentinel.next is going to be the real first item, if there is one. Now, if we want to actually go through and create an empty S list, what's going to be different, other than this being called Sentinel, is that we need to make a node. There should be something there, the faithful companion, and we said it needs to be comma null. If we look, question mark null. But in Java, you can't set question mark. So instead, I'm going to pick any old number. And it doesn't matter because the faithful companion, we're never going to ask the faithful companion's opinions. It's just going to hold some data. So I'm going to put in 63. Okay, good. Doesn't matter. I mean, you could have picked -5, but I picked 63. That's that for empty S lists. How about for the one-item S list? Well, in that case, the sentinel is still going to have the same faithful companion at the front. And then the faithful companion is going to point at the data we want. It's going to say, hey, you want data? Here's the naked recursive data structure, the first node of it. All right, that's S list. How about add first? Okay, so sentinel equals new int node x sentinel. I'm going to say this is wrong. The reason it's wrong is that sentinel should be pointing only at the same faithful companion. We should never be reassigning sentinel. Instead, we should be saying, hey, sentinel, someone wants to get in line behind you. Oh, do they? Okay, great. Sentinel.next equals new int node x, sentinel.next. So the idea is that whoever used to be at the front of the line is now second in line. Then we have get first. So if I want to get the first item, this is also wrong, even if I do sentinel.item. Why? We look back at this little note we have. The first item, if it exists, is at sentinel.next, not sentinel.item. So the problem here is that we're asking the sentinel for its opinions, but it's our faithful companion, never need be spoken to. So the sentinel should be saying, you know what? Don't ask me my opinion. This is who you're looking for. and the virtuous Sentinel gets the data to us. Thank you, Sentinel. And then finally add last. So in this case, the Sentinel is never null. We always have the companion. May as well delete that. We'll say p equals Sentinel. So we start at the Sentinel, and we have the pointer walk the negative recursive data structure starting at the Sentinel. And as long as p.next is not null, we go to the end of the list, and it may be that p is just the Sentinel because we only have no items in the list at this point. And then once that's done, we do p.next equals new int node. And that's it. We're done. Now, was that easier? It might have seemed harder. It seemed like we had to do a lot of changes, that it seemed complicated, that we had something that already worked before. But in larger systems, I promise you that this will make your life easier. And when you get to building the linked list-based deck in Project 1, I highly recommend that you build it using Sentinel nodes like this. So let's run this thing through the visualizer, make sure that everything behaves the way we expect. And this is not a thorough test, but we'll just get a rough picture. So after we've created the one item Sentinel, the one item list, okay, here we go. This is the 0 item list. Then we have our variable L points at our middleman, has size 0, and Sentinel points at our faithful companion, who you see is holding the number 63. After we add the number 20, it ends up at the end of the line after 63. So that's basically that. So let's summarize what we accomplished. The Sentinel node is a dummy node, a faithful companion, again, to use the same phrase, that's always there for you. Now, given that first is no longer pointing at the first item, I've renamed the first variable to be Sentinel. And Sentinel, of course, with all the code we wrote, it's never null, and it always points at the Sentinel node. The Sentinel node's item needs to be some integer. I picked 63. You could have picked whatever you want. And then as we wrote our code and looked through each of our constructors and methods, we had to make sure everything was compatible with our Sentinel nodes. And ideally, you would have done this from the beginning, so it wouldn't feel quite so haphazard. It wouldn't be a bunch of minor changes that we're making all at once. So the bottom line here, just to summarize what we did, we had the issue that some S lists had a null first and some didn't. So we fixed this by bringing everything under one big, consistent, beautiful heading. Everything is handled the same way. There's no need to think about special cases. Because we make sure that we always have the faithful companion list. It eliminates the need for this special case and makes our lives ultimately easy.